Hello, everyone. Today we're having Christian Korff, and he's going to talk about the asymmetric six-vertex model and cylindric Hecke characters. And I'm very excited about today's talk. Thank you, everyone, for coming.
Thanks very much, Slava. And let me just start by thanking you for the invitation and also for setting up such a fantastic website and resource. I think that's really a great service to the community. So on behalf of everyone who is working in this area, many, many thanks. So I'm going to talk about things which you have heard in the seminar series before, probably some of the very familiar topics to you by now. So the six-vertex model, and I call this the asymmetric version. I think by just looking at some of the talks which have been given in the seminar before, this is also sometimes called the six-vertex model in external fields like electric or magnetic fields. So all what this means is that there's an asymmetry in the Boltzmann weights which you assign, but I'll come to this later. And then I'll talk about cylindric Hecke characters, and you're not supposed to know what cylindric Hecke characters are, but I will basically start out by first reviewing what Hecke characters are. So the Hecke algebra will play a role. And if you, after the talk, are not discouraged from going deeper into the topic, you can read things up. So this is published here in this journal reference. Okay, so with any further ado, so the outline of the talk will be a quick reminder about Macdonald's characteristic map, which I think hasn't featured before here in the seminar series, but you have certainly heard about the boson-fermion correspondence before, and some people here in the audience have used it in their work. And then I will try, so this is usually set up in the context of the symmetric group, and we will then try to generalize the setup to the Hecke algebra, which you can think of as a deformation, as a quantum deformation of the group algebra of the symmetric group. And we will do this in order to make actually contact with the asymmetric six-vertex model. I will briefly talk about vertex operators. So again, as I'll come to this in the talk, but again, people here have worked on this. So in the context of Leclerc, Lascaux and Thubon polynomials, the vertex operators have been constructed using the six-vertex model. These vertex operators, which I will talk about briefly, are related to Hall-Littlewood polynomials. And then finally, this is really for me the most important new result which came out of this work. It's the realization of the cylindric Hecke characters within the Grothendieck ring of all Hecke algebras, where they form a subcoalgebra. I define all this, which has structure constants which are non-negative integers. And whenever this happens, you want to find a nice combinatorial interpretation of these structure constants. And in this case, it's a geometric interpretation. So they are Gromov-Witten invariants for Grassmannians. Okay, so let me just start with Macdonald's characteristic map. And the main players here are Rn. So think of this just as the vector space of class functions, which you can identify with the Grothendieck group of finite dimensional modules of your symmetric group. So the n here is just meaning that this is really the set of class functions of the symmetric group on n letters. And then we're taking the direct sum because in a moment we will introduce a product which will be done via the induction functor, which I will explain briefly. And that basically means that you have not just to consider one symmetric group, but all symmetric groups at the same time. And on this side, we have, for the same reason, because of the product which we want to introduce, we have the sum over all the centers of the group algebra, and there's a natural vector space isomorphism, which takes you from the class functions to the center of the group algebra of the symmetric group. And then there's the so-called Frobenius map, which maps a canonical basis in the center down to the ring of symmetric functions, which by now, if you have followed the seminar series, you know there's a close tie between symmetric functions and the solvable lattice models. And Macdonald defines this characteristic map, which takes a irreducible character. So the characters are special examples of class functions, and the irreducible characters in particular form a basis of the vector space of class functions for Rn. And Macdonald's characteristic map just takes such an irreducible character and sends it to a Schur function. So let me just repeat this and just show you. So in each of these corners of this triangle, we have vector spaces which have distinguished bases. And as I already said, so in this direct sum of all class functions, we just want to take the irreducible characters, which come from the irreducible modules of a symmetric group, which are called Specht modules. So lambda, if it's a partition of n, then this gives you an irreducible module of the symmetric group on n letters. Then here the center of the group algebra also has a distinguished basis, namely just you take the sum over conjugacy classes of your group elements. In this case, these would be all permutations of a fixed cycle type, where lambda is again a partition of n. And then down here in the ring of symmetric functions, we have actually now two distinguished bases which we will need. One is the basis of power sums. So what you would do is, for instance, you would take such a conjugacy class which lives here in the center and map this under the Frobenius map to a power sum modulo a certain factor, which is just the size of the conjugacy class. But Macdonald's characteristic map does something different. So it takes the irreducible character of your Specht module indexed by lambda and sends this to a Schur function S lambda. And the statement is that these vector space isomorphism that this diagram commutes. So in particular, if this triangle commutes, this means, for instance, that then the Schur function, which is your image, right, under the characteristic map of an irreducible character, that this must be expressible in terms of the characters, of the irreducible characters of your symmetric group. And I just noticed a small typo, so this should be for consistency in upper index. So what we are getting is this inverse Frobenius formula, which expresses the Schur functions in terms of power sums, and the basis transformation is given by the character table of the symmetric groups. And that's basically what this commuting diagram tells you. And as I said, we would like to generalize this where we replace the symmetric group algebra, the group algebra of the symmetric group by the Hecke algebra. But before we do this, let me maybe also first, on the simple example of the symmetric group, introduce a Hopf algebra structure. What is really just important for us is that there's a product and a coproduct structure. So how does this work? So you probably know that there is a natural embedding of the direct product of the symmetric group on M letters and the symmetric group on N letters into the symmetric group, which has M plus N letters, right? So you just identify these with all the permutations which permute the first M letters, and these with all the permutations in the larger group which permute the last N letters. So that's a natural group homomorphism. And you use this in order to define an induced module. And this is what the induction functor is. So it basically allows you to take two reducible modules or reducible characters from two different symmetric groups, and then define a character, the induced character, for the symmetric group from n plus n letters. And that is the product which we are introducing here on this direct sum of all these vector spaces of class functions. And you can see now, right, that we need to really take the sum over all n, because this product does not preserve the number of letters, but there's a graded structure here. Excuse me, sorry. But of course, we can also go in the opposite direction. So if I give you an irreducible module of the symmetric group as n, now with large n, you can decompose this or restrict it, sorry, to the subgroup of Sm cross n, where m plus n is equal to capital N. And this is giving you a map which goes from Rn into the direct sum of the decompositions, so tensor products of these. And this is what is called a coproduct. It goes in the opposite direction. And what you do is, so before we had vector space isomorphisms, but it turns out that you also have Hopf algebra isomorphisms here. So these maps also preserve the product and the coproduct. It is quite complicated to describe this directly in terms of these centers. So here, basically, just think of defining the product and coproduct such that the vector space isomorphism, which we had before, becomes a Hopf algebra isomorphism. So you just define the product and coproduct on this direct sum of centers so that it becomes a Hopf algebra isomorphism. But the non-trivial information is really here in the characteristic map, because if this is really a Hopf algebra isomorphism, this tells us that the problem of computing in induced character, meaning that you try to compute the decomposition into irreducible characters, that this can be actually done down here in the ring of symmetric functions, where a lot of combinatorial algorithms exist. So the product structure, which we have up here in this ring, is just the multiplication of two Schur functions, and the expansion coefficients are the Littlewood-Richardson coefficients, which you will have heard of. The important thing is simply that we have now explicitly shown why these should be non-negative integers, because they are just coming from the problem of reducing an induced module into irreducible ones. And because this must be direct sum, right, we are expecting non-negative integers. So that's the value here, if you like, of making this representation theoretic connection between the class functions or the finite dimensional modules of the symmetric groups and the ring of symmetric functions. I can get the same coefficients, the same Littlewood-Richardson coefficients, also via the coproduct. And this is actually the route which I want to choose. It's a bit unusual, but you don't lose anything. So you get the same information from the coproduct. And the reason for this is that the Hopf algebra, if you look at the ring of symmetric functions as a Hopf algebra, is self-dual, meaning that the coproduct has the same structure constants as the product. And what you do here is, so your coproduct, which I denote by delta acting on a Schur function, is just the sum, where you have in the first factor appearing now a skew Schur function, and the sum is over all partitions mu, which fit inside the Young diagram of lambda. And you might know this if you are on top of your game with Schur functions, that the skew Schur function can be rewritten in terms of normal Schur functions by using the Littlewood-Richardson coefficients. So if I would plug this expansion into the coproduct, you would see, right, that you would get by this coproduct the same structure constants as you would get from the product. It's just that the indices have been permuted. Okay. So we can actually think of the ring of symmetric functions as a combinatorial model for this Grothendieck ring of the symmetric group via Macdonald's characteristic map. However, when you really come to the computation of characters, let's say, you use a combinatorics which actually does not really originate either from here or from the ring of symmetric functions, what you use usually is a combinatorics, which involves fermions, and that's where the boson-fermion correspondence comes in. So you introduce another player, another vector space, which is called the fermionic Fock space, and which you have heard before in the seminar series. And you can think of this as a infinite wedge space. I talk about this a little bit more in detail. So think of basically an infinite long antisymmetric tensor product of this vector space where the basis is just labeled by integers. And then on this fermionic Fock space, you have a certain algebra acting, which is called Clifford algebra. And physically, you would interpret this as fermion creation annihilation operators. And this boson-fermion correspondence maps so these bases. There's a distinguished basis here, which are these half-infinite wedge products, and maps it again to Schur functions. And it has received a lot of attention because of connections to classical integrable systems. The boson-fermion correspondence is so-called Kadomtsev-Petiashvili hierarchy. And from a representation theoretic point of view, it's a Heisenberg algebra homomorphism, which is just you look at the action of the power sums on your ring of symmetric functions. So you can multiply by a power sum, or you can differentiate with respect to a power sum, because these are generating your ring of symmetric functions. And you can show that this gives you an action of a Heisenberg algebra. And you can cook up an action of the Heisenberg algebra in terms of these generators of the Clifford algebra. And then it turns out that this boson-fermion correspondence is defined in such a way that the action of the Heisenberg algebra is preserved. So let me maybe just quickly remind you about the fermionic Fock space. So as I said, so just think of this as a half-infinite wedge product. So these VIs are some basis vectors, which are labeled by integers. And the condition is, in order to make these half-infinite wedges well-defined, is that if you go far enough to the right, in my case, so if you increase the index on your I labels sufficiently far, then these labels just become a certain integer c, which is called the charge, minus k, which is just the position in this wedge. So in a sense, nothing happens after if you just go to the right in your wedge product far enough. And graphically, we can picture this as follows. So whenever I have such an element here in my wedge, I just draw like one of these black bullets. And if there's a gap between two consecutive labels of these infinite wedge vectors, I just draw like a white sphere. So what I have is basically an infinite set of white ghost stones. So I just adopt here the convention of talking about this in terms of Maya diagrams. And because this was heavily influenced by Jim O'Meara, I think I just talk about ghost stones. So you have on this side, you have everywhere white ghost stones. And then you have a region where you can have both black or white ghost stones intermixed. But if you go far enough to the left, everything will be black ghost stones. And this is what is called the Fermi sea. So my black ghost stones are my fermions. And where they are located on this integer lattice, that gives me these labels. These are basically just the position of my fermions in this one-dimensional lattice. And then this Maya diagram encodes a partition, a Young diagram of partition. Namely, what you do is for each black ghost stone, right, you just go like a step in 45-degree direction downwards. And whenever you have a white ghost stone, you go a step in 45-degree upwards. And this gives you then this outline of a Young diagram, and that fixes the partition. And the charge is basically just telling you where this Young diagram is balanced, right? So we balance this here somewhat precariously on its edge. And the boson-fermion correspondence takes such a configuration, which encodes your half-infinite wedge and maps this simply to a Schur function via this graphical identification, which I just told you, right? So you take your Go-stone configuration and you draw this little picture that gives you a lambda, and you just map this Maya diagram then to the corresponding Schur function. And you can write this map in terms of vertex operators, and that's where the KP hierarchy comes in. So you would consider this here your Hamiltonian, which you can express in terms of the Clifford algebra, but maybe I just skip about over this little step. So people who are interested in this, they can read this up in the lecture notes of Katz and Reiner. And there also, there's of course this book by Jimbo, Miva, and Date on solitons, where all this is described in much detail. Okay, so a little breather. If anything was unclear, now is the time to interrupt. So the summary is basically what I just want to repeat is that this characteristic map just explains to you that why the character table of the symmetric groups gives you the basis transformation between power sums and Schur functions. And that the Schur functions are a distinguished basis because their structure constants with respect to the product and the coproduct are non-negative, right? So we have these non-negative integers, and the characteristic map explains why, because we are relating this to the irreducible representations of the symmetric group, induced characters which get decomposed into reducible characters. But there's also a geometric interpretation which will play a role for the second half of this talk. Namely, you can also identify these Hilbert-Richardson coefficients as the structure constants of the cohomology, the intersection cohomology of the Grassmannians. So these are k-dimensional subspaces of an n-dimensional space. And this is precisely the aspect which I want to focus on later in the talk. I would like to generalize everything so that we get the structure constants of the quantum cohomology of the Grassmannians. And these are the so-called Gromov-Witten invariants. Okay, but let me maybe come to this problem of what I have now said repeatedly. How do we actually calculate the character table, which gives us the basis transformation between power sums and Schur functions? And this is the Monoham-Nakayama rule, which you can recast in terms of lattice models. So that's if we finally meet our hero of the talk, the six-vertex model. So the Monoham-Nakayama rule is just telling you that if you would like to calculate an irreducible character evaluated on a conjugacy class, which is of cycle type mu, then what you should do is you should decompose your Young diagram of lambda into ribbons, where the lengths of the ribbons are given by the parts of mu, of the partition mu. And if you do this decomposition into ribbons, every time you have such a ribbon, you multiply up a factor, which is just -1 to the power of the height of the ribbon. So that's how many rows it occupies in the Young diagram, -1. And if we use the boson-fermion correspondence and see what such a ribbon looks like in terms of modifying the Maya diagram, then what you will see here is on top is the Maya diagram, which corresponds to this black outline of the Young diagram. And then if I look at the red outline, then this is the corresponding Maya diagram here. And in between, I have now drawn a one-dimensional lattice of vertices, where each vertex is allowed to be one of these 6 vertices here, which belong to the 6-vertex model. And this is a very degenerate version of the 6-vertex model. You can see that many of the weights coincide. So think of these as Boltzmann weights abstractly, but X really is an indeterminate. And what you do is the usual thing. So you just multiply up all the Boltzmann weights for each vertex, and that gives you a weight function, or in this case, a polynomial in X, which you assign to such a configuration of two Meyer diagrams, which is connected by such a vertex configuration of the 6-vertex model. The other thing which I should maybe mention is that we also have imposed implicitly here certain boundary conditions, which are really important. Remember that I have the Fermi C on this side, and here I need to make a choice. There are different ways of how I could choose to connect the Fermi C. And what I've chosen here is that I always take a straight line, right? So I'm taking this vertex here, which just has Boltzmann weight 1. So even though I have like an infinite number of these vertices, because the weight is 1, they just multiply up this without any problem. And you can see if I would have, for instance, chosen this vertex, I would be in trouble, right? I would get an infinite power of the axis. So similarly to the right, where I don't have the Fermi C, but the, let me call it the C of emptiness. So where I have only the white ghost stones, right, I make the choice again of taking this vertex configuration, which again has a Boltzmann weight 1. So even though I have an infinite number of these vertices, again, the weight which I get out is still finite and well-defined. And the other observation is that in the Monoham-Nakayama rule, the condition is really that you just take ribbons, you decompose this into connected ribbons. But this, you can quickly convince yourself, means that you only look at very special configurations of the 6-vertex model. Namely, you can only allow one pair of these two vertices appearing. Because this vertex here, which is the half turn towards the right, this is the start of your ribbon. And this turn here downwards, that is the end of your ribbon. And if you would have, therefore, more pairs appearing, then you would have a disconnected ribbon. And this is, of course, the generic case of the 6-vertex model, but this doesn't come up in the Monoham-Nakayama rule. That you always need to have pairs of these two vertices occurring. You can convince yourself this is simply following from the boundary conditions which we have imposed, that we keep the vertex types fixed towards the right and towards the left in the Fermi C and in the C of emptiness. So clearly we would like to, inspired by the 6-vertex model, we would like to drop this slightly artificial restriction on the configurations and see what happens if we allow for arbitrary number of pairs of such vertices occurring. Right, and this brings us away from the group algebra of the symmetric group to the Hecke algebra. So the Iwahori-Hecke algebra of type A can be thought of as a deformation of the symmetric group algebra, but probably a more favorable point of view is to see the Hecke algebra as a quotient of the group algebra of the braid group of type A, where you factor out by the skein relation. So you have this quadratic relation here where T is some indeterminate or deformation parameter. So you see the Hecke algebra as an algebra over the rational functions in this indeterminate T. And I take the complex numbers at the moment for convenience. You could, of course, do it over the rationals. And then the other relations which you have is just a familiar braid relation. And if they are far apart, two generators, then they just commute. And now we just repeat this diagram which we had before. And thankfully, much of the combinatorics in decomposing irreducible modules is largely unchanged. So even though I now call this the quantum characteristic map, you still map irreducible characters of the Hecke algebra now to sure functions. So that map stays the same. But of course, the center will look markedly different. And the quantum Frobenius map will change. And this was worked out by Van and Wang in a paper. So the precise reference can be found in the bibliography of the article, which I quoted at the start of the talk. So up here you have a distinguished basis, which is more complicated. It's called the Guerre-Rouquier basis. But more importantly, this basis is then not mapped any longer to power sums, but to certain versions of monomial symmetric functions after a plastic change of variables. And that's what I want to describe next. So just as a reminder, everywhere appears now a small t. This is just a reminder that we change our base field from the complex numbers to the rational functions in T, which have complex coefficients. So that's all what this T means. So we have this change of base field here. So let me explain this plastic variable substitution in a bit more detail. So remember that in the case of the symmetric group, we had an expression of our sure function in terms of power sums, and the coefficients were precisely the irreducible characters of the symmetric group. And now this changes. So what I do is I take the monomial symmetric functions here. So these are now my images under the quantum Frobenius map, which I just mentioned, where this notation is just the notation of making a plastic variable substitution. So what you have to do is you have to express your monomial symmetric function mu first in terms of power sums. And in power sums, the variable substitution is just written like this. So if you substitute for your alphabet x, so if your initial variables were x1, x2, and so on, and you now basically use this notation here, what you should do is you simply multiply your original power sums, which are indexed by r, by this factor t to the power r minus 1. And then you use this, plug this into the expression of a monomial symmetric function in terms of power sums, and that gives you this function here. And this is now our image under the quantum Frobenius map of a element in the center of the Hecke algebra. And if you expand your sure function in terms of these substituted monomial symmetric functions, then what you find is that the coefficients are now given by the irreducible Hecke characters. And what I will do in order to make contact with the six-vertex model, I need to undo this plastic variable substitution. So what I want to do is this t dependence, which I have smuggled in here in the variables of the monomial symmetric function, I just smuggle into the variables of the sure function. So what I do is, right, I just do the inverse of this variable substitution. You still get as the expansions, as the expansion coefficients, the characters of the Hecke algebra. Now you have your standard monomial symmetric function here, but this side has changed. So under this plastic variable substitution, the sure function is now no longer the ordinary sure function, but it is the sure function which you get, which is dual with respect to the inner product for Hall-Littlewood functions. So I don't know, I mean, how familiar people are with this, but so Hall-Littlewood functions are special cases of Macdonald functions. And you introduce a certain inner product in the ring of symmetric functions with respect to which these two versions of Hall-Littlewood functions called P lambda and Q lambda by Macdonald, with respect to which they are orthogonal. And this is not the standard Hall inner product in the ring of symmetric functions, but a slightly different one, which depends on this deformation parameter T of your Hecke algebra. And if you then ask yourself with respect to this new inner product, what is the basis which is dual to Schur functions, then you precisely end up with these guys. I hope this was more or less clear. It's a bit technical, I'm afraid, but so just think of this as a T deformation of your ordinary Schur function. And we also need to deform our fermionic Fock space, because remember that the combinatorics which we want to use in order to see the six-vertex model involves these Meyer diagrams, which are described in terms of the Clifford algebra. So all what I do is, again, I just change the base field of my fermionic Fock space. And now the statement is that I change the boson-fermion correspondence by taking matrix elements of my, what I call the six-vertex transfer matrix. So this is just the sum over all possible lattice configurations. So I have like this one-dimensional infinite lattice, which has a Meyer diagram on top and a Meyer diagram on the bottom. And then I try to connect this with all possible six-vertex configurations. And I sum over these. And the claim is, if I multiply up all the Boltzmann weights for each of these configurations, sum it all up, then what comes out is this T-deformed Schur function. And the Boltzmann weights, which I take, they are very close to the Boltzmann weights which you have seen in previous talks. So for instance, on the talk about Tokuyama ice. So this is going back to this work by Ben Buberke, who's here, Daniel Bump, and I don't know the first name of Friedberg. So it's very closely related. The change here is in these two Boltzmann weights. So it's not quite Tokuyama ice, which we have, but it's very similar. And of course, also use slightly different boundary conditions than in this work, because I'm on this infinite lattice and we have fixed the vertices on these two sides to be very special vertices, namely these empty vertices and then these straight lines. And that's why I'm not getting out these other symmetric functions or these characters which Tokuyama introduced, but I'm getting out this T-deformed Schur function, which is related to the theory of Hollittlewood polynomials. And moreover, so these vertex weights and the configurations, they nicely now describe the combinatorics of computing these irreducible characters of the Hecke algebra. So as I said before, in the case of the symmetric group algebra, right, so now we are allowing for these path configurations with these turns to occur several times. So here, for instance, you see now two such pairs of these vertices which have these half turns in them occurring. And indeed, therefore, you have two disconnected ribbons. And the new choice of Boltzmann weights, which we are taking, just give us precisely the correct statistics which we need in order to calculate the character of the Hecke algebra. And what we're interested in is, first of all, the number of ribbons which occur. They basically determine the power of this prefactor T-1. We are still recording the height of the ribbons. So that's why the minus sign here is still in this Boltzmann weight. But now we're also recording the width of each ribbon. So that's what the T is doing in this factor. And then you can check, so the bijection is pretty straightforward. So here's an example. So here's a decomposition of a Young diagram into ribbons, into disconnected ribbons or broken rim hooks. And you can then verify that the statistics which are introduced is precisely the formula which was first written down by Rahm how to compute these irreducible Hecke characters. And the bijection is just, so take one of these path segments, which are formed by the six-vertex lattice configurations. So now we are doing one row after the other. And then you see that you have one horizontal edge in row 1, 2 horizontal edges in row 2, 1 in row 3, and then 2 again in 4. And that is precisely the first row of this ribbon tableau, right? So you see that this is 1, 2, 2, 3, 4, 4. And then you go to the next pass and you do the same, you follow this path also via the horizontal edges, and then you get the second row and so on. So the bijection is pretty straightforward. And as a byproduct of this, we can then also make contact with vertex operators and transfer matrices. So we have now described on the fermionic Fock space side what the combinatorics is to calculate these characters by the six-vertex transfer matrix. And it turns out that this six-vertex transfer matrix can be identified with a half-vertex operator. And half-vertex operators which occur in the theory of Littlewood polynomials. And they then match precisely the bosonic vertex operators which were written down by Jing. So Jing wrote down these vertex operators in terms of power sums. You can, for instance, also find them in Macdonald's book on symmetric functions. So you can see here that these are exponentials which involve multiplication by power sums and differentiation with respect to power sums. And they have now these additional factors which involve powers of t, which becomes because of the placistic variable substitution which we have done. And the statement is then that our six-vertex model now gives us a fermionic description if I combine the inverse of my transfer matrix with its adjoint. So I'm doing this here in the fermionic Fock space, apply the boson-fermion correspondence, and out comes the bosonic vertex operator. And you can do this for both types of vertex operator, which have been written down by Jing, the phi plus and the phi minus. And if you then apply these in the ring of symmetric function on the trivial symmetric function, which is just the identity, you get the whole Littlewood function. And you might be worried that you have to actually take the inverse here, which might be something which is incredibly non-local. But in fact, it turns out that the inverse is really just given by change in the local Boltzmann weights. So it's really, the fermionic description remains very nice, very, very local. All what you have to do is you have to change your Boltzmann weights. And I have here with these red arrows indicated which weights I have changed. So the inverse of your transfer matrix is just a new transfer matrix where you basically change your t to a t inverse and you replace your x with tx. So that was a bit of a surprise. And this is in spirit very similar to what people here have done in the context of what I mentioned before, the Lascaux, Leclerc, and Thibon polynomials. Okay, so in the remaining minutes of my talk, I now want to say goodbye to infinite lattices and go to something which I'm way more familiar with, namely periodic boundary conditions. So in physics, you usually like periodic boundary conditions because you get something like translation invariants back. And in particular, you can diagonalize your transfer matrices via a method which is called the beta ansatz, which can be extremely helpful. And our reason to introduce periodic boundary conditions will be of a more combinatorial nature because, as I said, I would like now to make contact with the geometric interpretation which we had before. So the Littlewood-Richardson coefficients were intersection numbers of the cohomology of Grassmannians. And now I would like to generalize this to the quantum cohomology of Grassmannians and yet Gromov-Witten invariants, which count certain algebraic curves connecting Schubert varieties. I'm not an algebraic geometer. I just threw there like a number of technical terms at you, but don't worry. We will just give a combinatorial description of these Gromov-Witten invariants using this lattice model. So what we do now is we're taking our infinite lattice and we're just forcing this onto a circle in the horizontal direction. So we're working now on a cylinder. And what I would like to define is a projection map, which takes me from my Fock space, which we had before, my Maya diagrams, and I now fix my charge to a certain integer value, which I call k. And this k will be the dimension, later on, will be the dimension of the hyperplanes in my larger dimensional space, my ambient space, which describes my Grassmannian. So this k here, the charge, will be identified now with a finite batch product of a finite dimensional space, which is just Cn, where n is the circumference of my cylinder. So I'm taking only n lattice sites. And I take the same Boltzmann weights as before for my six-vertex transfer matrix. So nothing changes. So I take, as for the Hecke characters, I take the same Boltzmann weights. The only difference now is, as I said, that I'm summing over configurations which are which satisfy periodic boundary conditions. And to make it slightly more interesting, I make these quasi-periodic boundary conditions. So I remember basically where I cut open my infinite, my one-dimensional infinite lattice and glue it together in order to get a cylinder. And whenever this happens, that there's one of these hydrogen atoms, these blue balls on the lattice edge where I have cut my lattice open and then glued it together in order to get the cylinder, then I simply multiply with Q. I probably needlessly said this in a very complicated manner. So the Q is basically just counting how often you go around your cylinder. So think of the Q of just keeping track of a possible winding number, because we have now a topological non-trivial lattice. That's all what the Q does. Okay, that's actually all I wanted to say about this. So we're taking this transfer matrix. And then, as I said, so the nice thing, once I go to this finite dimensional setup, we have now quite a finite wedge of a finite dimensional space. Then my transfer matrix becomes diagonalizable. And indeed, in the case which we are working here, which is known as the free fermion case, so our six-vertex model, which we are looking at, is very special in terms of the Boltzmann weights. That we can actually find the eigenvectors explicitly and also the eigenvalues. And once you turn on this machinery, you can show that the eigenvalues are of this form. And they are parameterized in terms of certain complex numbers, these yi's, which are called the beta roots, which you can see are, if I would set this twist parameter Q, which is just keeping track of my winding around the cylinder, if I would set this to 1, and these would be just certain roots of unity. And this prefactor here is important. It inspires me in a sense to define a renormalized transfer matrix. And I explain this a bit better in a moment. So what I would like to do is, it falls a bit from the sky at the moment. I would like to simply divide out this factor, which is appearing here in the eigenvalues, because this only depends on the circumference of my lattice. And K is just the number of hydrogen atoms which I have on the vertical upper edges. So this is actually preserved by the transfer matrix. So the transfer matrix, of course, does not change the number of lattice sites n, and it also keeps the number of hydrogen atoms which are on the vertical lines fixed. So I divide by this, and one way of looking at dividing by this is look at this as a geometric series. So once I write this as 1 over 1 plus minus 1 to the power k q to the x and tn, you can write this as a geometric series. And this is just a factor which arises from going several times around your cylinder. So what I'm dividing out here is basically the possibilities of winding around the cylinder. Okay, so this is renormalized transfer matrix, which I still owe you a better explanation for. So remind me if I should forget. I now just come up with a generalized definition of my Hecke characters, which is inspired what we did before on the infinite lattice with open boundary conditions. So what I do is I decompose my transfer matrix as a polynomial in my spectral parameter x, which entered the Boltzmann weights, and I just look at these operators which I get as the coefficients of this polynomial. And I then take matrix elements. And we did precisely the same thing before, and we would have gotten out a normal irreducible character of the Hecke algebra. But now, because I'm on a cylinder, everything will also depend on how often I go around the cylinder. So there's a dependency on a d. And because everything is on a cylinder, I don't get any longer arbitrary partitions lambda and mu. My partitions lambda and mu now live in a bounding box. And the bounding box has 2 dimensions. One is k, is the height, which is just the number of hydrogen atoms on the vertical edges. And the other one is n minus k, where n was the circumference. So my partitions lambda and mu now must lie inside this bounding box. And similar as for the normal characters, you can derive from this definition certain recurrence relations, which allow you to calculate the cylindric Hecke characters explicitly. So if you like, this is a generalized Monaham-Nakayama rule for Hecke characters on the cylinder. So I'm jumping over this bit because I would want to come to the punchline. I'm also mindful of the time. So the main result is then that the cylindric Hecke characters, which I have introduced by simply imposing these periodic boundary conditions, that they form a closed subcoalgebra under this coproduct which we had before, which is just the restriction function. So what I do is I just look at the cylindric Hecke characters where one of the partitions is just the empty partition. I have this integer d, which is telling me the winding around the cylinder, and I have a partition lambda, which is inside this bounding box of these dimensions. And if I then apply the restriction functor to this cylindric Hecke character, you can write it again in terms of cylindric Hecke characters, and the coefficients which you get are non-negative integers. And you can show that these non-negative integers are now indeed the 3-point genus 0 Gromov-Witten invariants of the Grassmannian. So I promised you a bit of a combinatorial formula for these, and it's a bit hidden, but it is basically just in these recurrence formulae for the cylindric Hecke characters, which you can compute by taking matrix elements of your 6-vertex transfer matrix on a cylinder. So what this is telling me here is that I have constructed a positive coalgebra within the Grothendieck ring of my Hecke characters, of my Hecke algebra, sorry, which is closed under this coproduct, the restriction functor, and whose structure constants are all positive and also have a geometric interpretation. So I think I have 4 minutes left. So let me motivate this a bit more so that it doesn't fall completely from the sky. So this was really motivated by previous work with one of my PhD students, David Palazzo. So what we can ask after we have defined the cylindric Hecke characters, we can ask, well, we have the characteristic map of Macdonald, which tells us how to map the cylindric Hecke characters which live up here, how to map them into the ring of symmetric functions, and what are the symmetric functions which come now out of this. So before, right, we saw when we had the infinite lattice without periodic boundary conditions, we just got this T deformation of a Schur function, which was related to whole Littlewood polynomials. So what do we get now with periodic boundary conditions? And what we are getting are so-called cylindric Schur functions. And that is the work which I mentioned. So together with David, we use different combinatorial methods to show that the cylindric Schur functions form a positive subcoalgebra in the ring of symmetric functions, which indeed had also the Gromov-Witten invariants as structure constants. And was unsatisfied basically with the combinatorial description of this coalgebra, and I wanted to find like a nice lattice, integrable lattice model description of them, and this was only possible by going back to the Grothendieck ring of Hecke algebra. So that's the motivation. So let me maybe in the remaining minutes to say a little bit about cylindric Schur functions. So originally they were introduced by Gessel and Grattenthaler. In the paper which I've written, I use the notation of Postnikov, and there are many other people which have worked on this. Among them Lahm, so Lahm generalized cylindric Schur functions to affine Stanley symmetric functions, which some of you might have heard of. And there's other work, in particular of Peter McNamara, who conjectured that these cylindric skew Schur functions were positive if you expand them into cylindric Schur functions, which is precisely what comes out as a result if you show that cylindric Schur functions are positive coalgebra. So the cylindric Schur functions which you get under these under the McDonald's characteristic map from cylindric Hecke characters are simply defined by drawing your bounding box. So in this case, k is 2 and n minus k is also 2, so n is equal to 4. And I've taken here the Young diagram of the partition 2, 1. And then I periodically continue this bounding box and just make infinitely many copies in the plane. And this gives me the outline, which I have drawn here in gray. And this is what is called a cylindric loop. And on this cylindric loop, you can define an action of the affine symmetric group. And in particular, the affine symmetric group also has certain translations acting. And these translations shift these cylindric loops in the plane. So for instance, you see this red line here, which I'm now wiggling around. So if I put this here on the gray line, you see that this is precisely the cylindric loop I started out with. But under a translation of the affine symmetric group, you shift this diagonally in the 1 + 1 direction. And you see that you get a bigger cylindric shape. And you start filling this bigger cylindric shape in order to get a cylindric tableau. And these cylindric tableaus, they now have more constraints than your original tableau, which was just in these bounding boxes because of the overlap. So if you now fill your rows and columns, because there's this overlap, so you see that you have to do this in a periodic manner, you can see that, for instance, this must be a 3 if I have on top of this a 2, right? So you need to have this strictly increasing in order to get a semi-standard tableau filling. So via these periodic conditions, you get only very special tableau which satisfies these cylindric boundary conditions. And amazingly, if you sum up over all these cylindric tableau via the usual weight functions, you get a symmetric function, and this symmetric function is precisely your cylindric Schur function, and that is the image which you get from the cylindric Hecke characters under the characteristic map. And now I'm 2 minutes over time, and you must be tired, so I better stop here. So thanks very much for listening, and I hope that I didn't put everyone to sleep. So if you have questions, please ask away.
Yeah, let's thank the speaker.